In this lecture, I will talk about generating uniform random variables. I will talk about project management, simulation of project networks. I will a little bit talk about central limit theorem. I will talk about importance of coordination between activities. I will talk about importance of coordination between technical precedence of activities and the resources they do need, resource allocation. In project management, those who developed PERT system, program evaluation and review technique, they assume that duration of activities follow beta distribution. And then triangular distribution is a good distribution to estimate beta. So usually when we simulate a project, we use triangular distribution. But for the sake of simplicity and to be able to deliver the concept, in this talk I will use uniform distribution. Later in another talk, I will use triangular distribution and I will simulate a project network using triangular distribution. If you need the PowerPoint slides, you may go to this link. I do have about 150 slides over there, which I have developed for different continuous and discrete probability distributions for their applications. Let us start with this project. Two activities, activity A and activity B. Average duration of each of these activities is 40 days. But this 40 days is just the average. The actual time has uniform distribution with bounds of 20 and 60. Let me go to this Excel sheet. Here I am going to generate duration of the first activity and then duration of the second activity. In most of programming languages, we do have something called uniform random numbers. Uniform random numbers are numbers between 0 and 1. In Excel, we just need to type equal to rand, parentheses. Then a number between 0 and 1 is generated. I can take this number to any other interval. For example, here we want to have the smallest value of 20. So what I will do, I will go here and add 20 to this number. Now this function creates something between 20 and what? 20 and 1. Because it is 20 plus a random number. And that random number has a minimum of 0 and a maximum of 1. But something between 20 and 21 is not what I want. I want something between 20 and 60. Therefore, I want, when my random number is 1, the duration of my activity to be 60. and I have already added 20 units to my random number. So all I need is to go over there, open a parenthesis, and then say 60 minus 20 multiplied by rand. Now, if rand is 0, it is multiplied by 40, is 0, and then it's added to 20, it will become 20. If rand is 1, it will be multiplied by 40, and it will be 40, and it's added to 20, it will become 60. Therefore, now, each time I click, a number between 20 and 60 is generated. Oh. So I go here, I type equal to 20 plus the gap between 60 and 20, which is 40, multiplied by rand. And that will create a random number between 20 and 60. And then I can copy it down, and then I can copy it here and copy it down. All of these numbers are something between 20 and 60. They are not integer, but I have made this with no decimal points. So they are not integer numbers, but if I reduce integer, the duration of project is equal to duration of activity A plus duration of activity B. And then I copy it down. Now let's collect some information about duration of this project. The minimum duration for this project is 42 days. The maximum is 119. The range is the difference between these two. Let's see. Here we assume that we need something around 10, 11 categories, but I have another lecture on histogram. That video is more explanatory regarding how to create a histogram. Frankly, 7.66 is not an appropriate width. Round it 0. 8, the width of each category. Then minimum is 42, and it has also some decimal points. Equal to this minimum divided by the width. So I find it out, round it down to 0. My minimum is around 5 times width, and then I multiply it by the width. Right? So I now have a clean starting point for my categories. I do the same for max, but here I will round it up, and therefore that would be max divided by width rounded up multiplied by width itself, and round it up to 0. Average of all the numbers. So the project duration is 80 days. That is what we expected, because the average of this one is 40 and the average of this one is 40. So the average we expected to be 80 here. But later I will discuss, due to interdependencies between technical dependency of activities and resource dependency, the time will be more than what we may simply think about this specific project. Standard deviation, we compute it as usual, and coefficient of variations is standard deviation divided by average. Now I would like to create a histogram and an S-shaped curve, or a cumulative curve. I'll delete this one. I will delete here. I go over there and type equal to count if. Count if. What range? Project duration. And lock it because I'm going to copy it down. What is the criteria? It is less than and second number. I cannot get it. I go to the cell below it and then upper row, and that's it. This is the number of observations in that category, and then I copy it down. This is from 40 to 56, 74 observations. From 40 to 80, 524 observations, and from 40 to 116, 1,000 observations. Then I compute the percentages or frequencies. I get each number divided by summation, and I lock the summation because I'm going to copy it down. Copy it down. And then I want to find the frequencies in each category. First category is what it is. Second is the difference between these two. Enter, and then copy it down. Now I have frequencies in each category, and I have cumulative frequencies too. I'll go here, insert, chart, and I select this chart. Here on the left hand side on the vertical axis, I do have the frequencies, but on the vertical axis I have some numbers which do not have any meaning to me. So I'll go here, select the data, I go to the horizontal axis, edit, and then I go and select these numbers. Okay. Those are the averages of the lower limit and upper limit of each category. And then I say OK. Then I select the data, format data series, and then remove the gap. Now I have a graph like this. Again, I go over there, select data, add, and series name, cumulative, and here. OK. OK. Then I click on this one, change series data type here, and I say use a line, and then use the secondary axis for this one. Now the left hand side is used for the histogram, the right hand side vertical axis is used for cumulative graph. I can also go here, format axis, and because I know that frequency does not go more than 100%, I will change that line. Now one other thing I need to do, I'll go here, equal to quotation, project duration, average, equal to, and I click on average, and quotation mark, comma, space, coefficient of variation, space equal to space, quotation mark, and coefficient of variation, enter. The only problem is average and coefficient of variations have too many decimal points. So I'll go here, I type round this one to 1 and round this one to 2. That's it. Now I have a nice statement over there. Click on this. I'll go to this bar. I type equal to, and I click on this cell. Enter. Now project duration and average and coefficient of variations are there, and if I change my data, things get updated automatically. Let's take a look at two managerial observations. First, while this activity has uniform distribution and this activity has uniform distribution, the summation of the two activities doesn't have uniform distribution. It is closer to normal distribution than to uniform distribution. That is one interesting managerial observation. And that is what we refer to it as central limit theorem. When we add several random variables or average several random variables, the distribution gets closer to normal distribution. Why? Because up and downs compensate for each other. One other interesting observation we have is coefficient of variation of the project duration compared to coefficient of variation of each activity is smaller. Therefore, those up and downs also reduce the standard deviation of the summation of those numbers compared to the average of. However, the averages are more or less what we expect. We expect this average to be around 40, this average to be around 40, and this average to be around 80, and they are around those numbers, very close to those numbers. But coefficient of variation of the project is always smaller than coefficient of variations of each individual activity. Now let's talk about another interesting managerial observation by comparing this project with this project. What is the difference between these two projects? In a deterministic world, this activity should take average of 40 days. This activity should take average of 40 days. Therefore, they both should take an average of 40 days. So after 40 days, we should be here. And then this activity also takes 40 days. Therefore, the project should take a total of 80 days. That is exactly the same as our expectation here. 40 days, and a total of 80 days. If we were living in a deterministic world, but we are not. While the general rules in this universe, like the central limit theorem, are correct, things represent random variability. First, let me fix this graph by selecting data and saying show the hidden source. So we are going to compare these two projects and show that while in a deterministic world, duration of both projects should be 80 days, in real world, this number is not. So I'll come here, equal to 20 plus 20 minus 60, which is 40, the difference between upper and lower limits, multiplied by rand. Then I copy it down, and then I copy it here, okay? Let's see what is the difference between these projects. This is duration of A, this is duration of B. But C cannot start until both A and B are completed. And nth of both A and B is the maximum duration of A and B. both A and B are completed. And therefore the duration of project is equal to when A and B are completed plus duration of C, the duration of the project. Min, max, min, equal to mean. I mark these numbers and I lock it, but I relative lock it. I lock it from 2 to 1001, but not on A. So I lock this one. Now, if I copy it down here, all I need is to go and make this one max. Please note it is still from 2 to 1001 because I locked 2 and I locked 1001. And here I have average, so I again copy it down, average, and then again I copy it down and I type standard deviation of sample and then coefficient of variations. Look, A was not locked. 2 to 1001 were locked, but A was not locked. Some component of a cell are locked, the others are not locked. So while here we have A from 2 to 1001, but because A is not locked, then if I copy this, it will become B. So as we see, A, B, and C, they all have averages very close to each other's, and standard deviations very close to each other's, and coefficient of variations close to each other's. But now let's see when is end of A and B, which is start of C. If I copy these numbers here, interestingly, the average of both A and B is not 40. It is something around 46. And coefficient of variation is also smaller. And then for the overall project, okay, now in order to create the graph, I do something a little bit easier. Equal to rows. And then I click on this cell, semicolon, and the same cell appears. I will go and make the first one absolute. Then I copy it down. So now I have a numbers from 1 to 1000. Small, small. Small what? Small project. And lock it because you want to copy it down, and rows, small first, small second, small third, and so on. And then I will copy it down. This is the smallest duration of the project. This is the largest. And I'll go here and type rows, and I have 1000 numbers. So it's 1 divided by 1000, 2 divided by 1000, and so on and so forth. So I copy it down. Therefore, if I delete this one, if I click on these two, select data, and I can a little bit improve it. I can go here. There is 50% probability that I can finish this project in around 88, 87 days, 25% probability around 75 days, 75% probability around 98 days. There are, say, 80% probability that I can complete the project under 100 days. Now suppose we have a situation like this. We have technical interdependencies and resource interdependencies, as I explained. Here, technical dependencies state that activity A is immediate precedence of activity B, activity C is immediate precedence of activity D, both activity B and D are immediate precedence of activity E. The same as before, duration of all activities is uniformly distributed between 20 and 60 days. Indeed, you can look at this graph as a project or as a process. For example, a part comes from here, goes through 2 operations, another part comes from here, goes through 2 operations. They should be subassembled here in this last operations. Of course, over there will be not 20 and 60 days, but 20 and 60 minutes. But the logic is exactly the same. So we have 5 activities. Technical dependencies: A, immediate precedence B, C, immediate precedence D, B and D, immediate precedence E. We also have resource interdependencies. Both activity A and D need resource green, and we only have 1 green. Both activities B and C need resource red, and we only have 1 red resource. Therefore, technically, activity B cannot start until A is finished, and as long as the resource requirement is concerned, B cannot start unless C is also completed, because B needs the same resource as C. One day I also may talk about multitasking and show that allocating 1 resource at the same time to both these activities is not a good idea. Multitasking in projects is not a good idea. Okay, so D cannot start until C is finished technically, and also because we only have 1 green resource, it cannot start until A is also finished. We can look at this project like this. We can say both C and A are precedence to B, and for D, both A and C are precedence. Or we can represent them like this. There is a dummy activity. We cannot start it unless both A and C are completed. And dummy activity takes 0 time, and we cannot start B and D unless dummy, which takes 0 time, is finished, and then E could start only if both B and D are completed. All of them are representing the same logic. If we were living in a deterministic world, we would have expected that this one take 40 days, 40 days, 80 days, 40 days, 40 days, 80 days. At the end of day 80, we should have been here. 40 days, 120 days. The project should have been completed in 120 days, but as we will see, it will take more than 120 days. I'll go to the Excel sheet. As usual, equal to 20, which is the minimum duration, plus 60 minus 20, which is 40, multiplied by rand, and that is duration of activity A. I copy it down. The same for B, C, D, and E. So I copy all of them down. Now I have duration of all activities. start of B and D needs both A and C to be completed, because B technically depends on A, and as long as the resource is concerned, it also depends on C. D technically depends on C, and for resource planning, it also depends on A, because we only have one resource green and one resource red. Okay, let's see when both A and C are completed. It's equal to maximum duration of A and C. Okay. Therefore, if you want to know when A and C are both completed, in one instance it would be day 48, and we copy it down to get other instances. For B to be completed, we should have completed A and C, equal to completion of A and C plus duration of B. Enter, copy it down. For D to be completed, we need A and C both completed, and we also need duration of D. And then copy it down. End of both B and D is equal to maximum of B and D, which is not day 80, but day 86, and then copy it down. For project to be completed, we have end of B and D, then we should add duration of E, equal to end of B and D plus duration of E. Enter, copy it down. And that is duration of the project. Then I go here, and as before, I will type small. I mark the matrix of the project. 1 rows here is 1, and then it will become 2, 3, 4. Copy it down. Now I have all the durations sorted. This project may take as little as 74 days, or it may be as long as 176 days. So I have here average, standard deviation, coefficient of variations. Then here I have typed equal to quotation mark average, space equal to space quotation mark, and this one, and quotation mark, space coefficient of variation equal to space quotation mark, and coefficient of variation. The only problem is that coefficient of variation has too many numbers. Round to, let's see. So I can go here, select the chart, this side, add chart element, chart title, above the chart, select this one, go here, equal to, click on this, enter, and that is our project. The last thing I need to do, equal to rows. And then I click on here, go up, column, go to the first one, and lock it. So it says from L2 to L2, which is 1, but if I copy it here, it will be from L2 to L3. And because the first one was absolute, the second one was relative. Now if I copy it down here, is 1000, which is from L2 to L1001. Then I go here and type count divided by count from here to here, and lock it. That is the probability of project duration to be less than or equal to this, and to be less than or equal to this will be 1. If I copy it down, that's it. That is my graph. I'm going to go here a little bit, fix it. $80, $180. Okay, and here I know 1, so I make it 1. And I make my increment 25%. Therefore, this is my project. There is 50% probability that I can finish this project in about 132, 133 days. The maximum potential duration is 174 or something around that. The minimal 86. Finally, I can go here, copy, paste, and again, here I see that coefficient of variations in the whole project is much smaller than in each activity. Mean is 133.7 or something around that. And the standard deviation is 17 point something, coefficient of variation 0.13. In a future lecture, I will do the same thing for triangular distribution, because triangular distribution is a distribution which is used to estimate beta distribution, and beta distribution is what people believe that it is the best representation for activity times.